so far we have seen field created by dipole, potential by dipole, and in the last class we have seen some examples. So today we will see some more example of dipole, and after that we will start Gauss law. So in the last session we reached till this point, force on electric dipole in non-uniform electric field. So when dipole is placed in uniform electric field, it experiences 0 force, but the torque it experiences may depends on its orientation. So depending on the orientation, torque on dipole might be 0, maybe non-zero. But when it is placed in non-uniform field, so in 3 dimension I am keeping dipole whose dipole moment is given by pxi, pyj, pzk, and field in the space is given by exi, eyj, ezk, and I want to find out how much force this dipole will experience due to presence of this field. So situation might be something like this. We have got field this way in 3 dimension which is non-uniform, and a dipole is kept in a space like this. So this is representing dipole moment, and this is representing non-uniform field, and I want to find out how much force it experiences. We can easily calculate force using potential energy expression, and we know the potential energy of dipole placed in electric field expression was minus P dot E. So potential energy was minus P dot E, and if I differentiate this U with respect to R, then I will get force. So for force I can write in this format, which is nothing but, in the last class we have seen, this is nothing but d by dx I plus d by dyj plus d by dz k, and we have to differentiate u with respect to x to get the x component of force, u with respect to y to get y component, and u with respect to z to get z component. These all are partial derivatives, right. So partially we will differentiate potential energy with respect to x, y and z. So this will give me force, and I know the expression of potential energy, that I substitute here. So you can see this term, this whole term, if you look at this whole term will be differentiated with respect to x, this whole term will be differentiated with respect to y, this whole term will be differentiated with respect to z. So if you substitute the value of u, something like this you will get. So the whole term, partial differentiation with respect to x, partial differentiation with respect to x, then comes y, and then with respect to z we are differentiating all the terms partially, right. So this way we can find out force acting on dipole placed in non-uniform field. So today we will see some numerical to understand how to apply the concept. Let us see. So find the force experienced by dipole. So here we have got one point charge and a dipole, and I want to find out the interaction between these two. So as situation is simple, I can directly find out the force, because we know whatever force dipole exerts on the point charge, same force is exerted by point charge on dipole, direction opposite, Newton's third law. So one way of doing it, method 1. So this dipole creates field here, this is a field created by dipole, and at distance r the value of field we know 2 k p divided by r cube. So this is the field created by dipole at point charge. Point charge kept in the field of dipole experiences force. So, the force experienced by point charge, force experienced by this charge is charge into field created by dipole. So, the value of force from here I have q into 2 kp divided by r cube. This is method 1, simplest one, right. Now, see method 2. So, using the concept we have just discussed, this is charge q, and from here at distance r we have got dipole as the dipole moment is this way, dipole moment is this way, that means this is minus small q and somewhere here we have plus q, then only you will get direction of dipole moment the way it is given in the diagram, right. And from center of dipole this distance is r. Now, I want to find out force. So, this point charge say produces E field here at the center of dipole, this point charge produces field E in this direction away from the charge. So, this E is the field produced by Q. Let us specify it. So, I am calling this as E produced by Q charge. If you go further distance dr, the field here along the direction of increment of r I am assuming field is increasing, automatically with proper sign you will get, right. Obviously, when you go away from the charge field strength reduces, but to just make it mathematically simple, what I am assuming along the direction of increment of r everything is increasing. So, here in this case field instead of E q it will be E plus DEQ, and say somewhere here this will be EQ minus DEQ. So, now you can see if field at this point is in this direction, as this is positive charge, it experiences force charge into field EQ plus DEQ. Now, I am drawing free body diagram of this dipole. So, we are following method 2 and now we are drawing free body diagram of dipole. And this negative charge, as field is in this direction, magnitude is EQ minus DEQ, charge is negative, it experiences force in opposite direction. So, force it experiences is Q EQ minus DEQ, right. Now, if I ask what is the net force here, force net, so net force, this minus this, so Q DEQ plus minus direction opposite, we will subtract these two, if I simplify I will get this Q, E capital Q will get cancelled out and we are getting 2 times Q DEQ. if I multiply and divide by dr, if I multiply and divide by dr, dr here and dr here, this whole term will become dipole moment 2 times dr, this side dr, this is dr, so this total distance is 2 dr, right. This total distance two dr. So charge into 2 dr, charge into separation will give you dipole moment. So this is nothing but P into dq by dr. In the last slide we have seen we can directly write this expression. Here field is in x direction, we can directly differentiate with respect to x and multiply to the dipole moment, we will get the net force. Field produced by q, differentiation with respect to r. So this charge, this capital Q produces how much field? So field produced is kq divided by r square. If I differentiate with respect to r, I will get minus 2 kq divided by r cube. So this value if I substitute here, this is the field produced by q, right. So this q charge at distance r produces how much field? So this distance is r from here till center of dipole. So this distance is r. What is the field there? If I differentiate with respect to r, I will get this quantity dEq by dr, that I will substitute here, and what we are getting, dipole moment times 2k q divided by r cube. This is the force experienced by dipole due to point charge. And in method 1, see what we have got. So method 1 we are getting q times 2kp divided by r cube, and here also we are getting the same result. So you can solve this problem either by this method or this method. As here you know the field produced by the dipole and point charge was kept, you can directly write the field produced by dipole and get the force. Whatever the force experienced by this in this direction, same as the force experienced by this in opposite direction. Here minus sign is indicating minus sign, this minus sign, here I am writing magnitude only, right. Here this minus sign indicate that force is opposite to the direction of dr. So force on dipole because of this will be in this direction, and you can directly see that this charge produces large field here and a small field at far away point. As this field is large, this side force is larger as compared to this side force, and it will experience net force towards the charge. So if you release the dipole keeping this one fixed, it starts moving towards the charge. Similarly, if you keep the dipole fixed and release the charge, then it starts moving this way. So first simple situation is clear. When we have a charge and a dipole in a system, then how to find out force of interaction. Now what if we have two dipoles? Now we have got two dipoles, and I am asking what is the force experienced by this one on this one, right. So directly now I can write force is equal to dipole moment of 2 differentiation of field produced by dipole 1 with respect to r. Just now we have proved, right, same expression I can use here. So field produced by first one at distance r, field produced by this one at distance r, the formula of field produced is 2kp kp1 in this situation divided by r cube, right. If I substitute the differentiation of this one here, then I will get the force directly. So, this is the force experienced by second one, force experienced by second one due to first one. So, let us differentiate the function and get the force. That will be minus 3 when you differentiate it 2 kp1 divided by r to the power 4, that I will write here. So, what we are getting, force on 2 by 1 is P2 into, this will become 6, minus I will take in front, this will become 6 K P1 divided by r to the power 4. So, the magnitude of force is 6 K P1 P2 divided by r to the power 4, right. If I ask what is the potential energy of 2 when placed in 1, so here I am asking force, find force. If I ask torque and potential energy, torque, you can see that this will produce field along the dipole moment, and this negative charge will experience force in this direction and the positive charge will experience force in this direction with respect to center. As these two forces are passing through center, they are not providing torque. So, torque experienced by second one is 0. If I ask what is the potential energy, potential energy formula is minus potential energy of second one due to the presence of first one. So, potential energy of second one, it is dipole moment that we have to do the dot product with field, right. So, P2 magnitude as it is, minus sign, electric field produced by first one, electric field produced by first one at the center of dipole, that is 2K P1 divided by r cube, and the angle between them, field is in this direction and dipole moment in same direction, cos 0. Now we have got torque, we have potential energy, we have forces, right. So, this will exert force on this one, obviously you can see the direction of force, this will create the field in this direction, negative will experience more force as compared to positive one. So, this much force P2 will experience towards P1. So, if I draw free body diagram, as this force is more as compared to this one, the net force coming is in this direction towards first one, that is why we are getting negative sign here. Here I am writing magnitude of force. Same is the force exerted by this one on this one. So, I hope this one is clear, how to find force on dipole placed in non-uniform field. Now, what if I turn this one by 90 degree? Let us see one more example. So, second dipole is placed perpendicular to the axis of first dipole, this way. Now, I am asking find the force, right, and you can see that this dipole will produce field on the axis opposite to the dipole. So, here this will be a positive charge and this is a negative charge, and I assume that along the direction of r field increases. I already told you automatically you will get with sign, so you need not to worry about sign. So, this will create field, this blue one will create field here in this direction, and the value will be E minus d and here it will create field in the same direction. Assume with R field also got increased and now it becomes E plus dE and at center it is E. Now let us draw forces. So on positive charge force experience, on positive charge force experience I will just draw force, right. So on positive charge force experience will be along the direction of field. Now I am drawing force it experience, this is field. So force it experience will be Q times E minus D, and the force negative will experience will be opposite to the field. So force it experiences will be like this, that will be, because this is a negative charge, that will be minus magnitude only I need to write, direction I have already considered. So Q times E plus D. So if this is the free body diagram and I ask what is the net force, so subtract these two, F net is equal to this minus this. So E plus D minus E minus D. So free body diagram of dipole, this one is experiencing force in downward direction and this one is experiencing force in upward direction. Resultant of these two will give you net field, and if you simplify then again you are getting 2Q D. This is the field produced by second one. So let us write E2 so that there will not be any confusion. E2, this is E2, E2. So second dipole is producing field on bisector opposite to the direction of dipole moment, and accordingly we are drawing forces. Now what I will do, I will multiply and divide by dr. So if I multiply and divide by dr, so dr 2q, this is dr, this is dr, so 2 times dr into q will give you dipole moment, this is P1, d2 divided by dr, that means I need to differentiate the field produced by second dipole at first dipole. What is the field produced by second dipole at distance r? Formula is as this is bisector, it will be K P2 divided by R cube. Differentiating that will give me dE divided by dr is minus 3 Kp2 divided by R cube. I substitute that value here. So P1 times E2 d2 by dr. So d2 by dr is minus 3 Kp1 divided by R cube. So if I ask what is the magnitude of the force experienced by first dipole due to presence of second dipole, that is 3 Kp1 P2 divided by R cube. Direction, we are getting minus sign here, that means opposite to the direction what we have taken. Obviously this will produce more field here, so this force will be larger as compared to this force. So whatever direction we have considered opposite to that, we are getting force of this magnitude. Similarly, I can find out torque and potential energy. Just now we have seen this will produce field here in this direction, angle is 90 degree, potential energy will come 0, right. And with respect to this one, if I multiply, I will get the value of torque, right. Here it is producing field in this direction, and dipole moment in this direction. Formula is P cross E, PE sin 90, you will get the value of torque. So, now I hope everything related to the force experienced by dipole in non-uniform field is clear, right. Now, let us move to next topic. So, before we get into Gauss law, let us understand some important concept that we will be using in Gauss law. So, let us first understand what is area vector. Area vector. Any flat surface if you take, here we define area as a vector quantity. Why we are defining area as vector quantity, later we will understand, but for time being, if we are defining area as a vector quantity and we have got a flat surface. So, for a flat surface, we can consider outward direction like this towards u as a positive area vector, or we can consider this as area vector. So, for this board I can consider this as area vector, or I can consider this as area vector, both are equally good, right. So, for any flat surface, if I want to write area in vector form for an element, for this element if I want to write area in vector form, what I will do, I will write magnitude, that is ds in this case, what is the area of this element, right, and then I will add direction perpendicular to this element, this is n cap, normal unit vector. So, with magnitude if I add direction, this is the way we represent area vector. So, for flat surface you can take any direction as positive direction of area vector. Problem comes when we have a closed surface or curved surface, convex or concave. So, if surface is closed, outward is taken as positive. So, if I take say cylinder, a closed cylinder, curved surface and two flat surfaces, if I take cylinder and I want to define area vector for this curved surface. So, if you take a small patch over the area, which is curved, then outward is taken as positive. So, that is why here area vector is given by this vector perpendicular to the surface outward. Flat surface, as I told, flat surface, if it is not a part of any closed system, then any direction you can take. So, in this case you can take upward positive or downward positive, right. So, for this one you are free for this surface, you are free to take this as area vector or this as area vector. But when the same surface, same flat surface become the part of any closed surface, like in this case this flat is a part of this cylinder, outward is taken as positive, right. So, this is the direction of positive area vector. Similarly, for this flat surface, this is the direction of positive area vector. So, if surface is flat, not associated with any other closed surface, then any direction would do. but if it is a part of any curved surface, then outward is taken as positive. Let us take hemisphere. So, if I take a small element on the surface, then outward is taken with positive sign. I will draw the diagram again. What I am saying is, we have got a close hemispherical surface, right. So, if I take a patch over here, then this is the way we are defining area vector. If you take it over here, then it will be like this, outward and perpendicular to the surface. This angle is 90 degree, this angle is 90 degree, here these angles 90 degree, and here this angle is 90 degree, right. If I talk about this one, base, outward is taken positive. So, for this one, if I take a small element over here at the base, for this small element, this should be taken as positive direction of area vector. So, magnitude and multiplied to the direction, then you will get area in vector form, right. What's the use of that? Now, consider a situation through a pipe, water is flowing, this way water is flowing through the pipe. So, if I ask how much water is flowing per unit time, in fluid dynamics, amount of liquid flowing per unit time was represented by Q, that was nothing but d volume by dt, and that is given by area into velocity. So, whatever be the cross sectional area, if you multiply it to velocity, then you will get amount of liquid flowing, right. Here you have taken this as A, right, area of this cross section is A and the velocity of fluid is V. So, this velocity was V, right. Now, if I ask you find the amount of liquid flowing through this imaginary area, so instead of taking this one, if I take the same magnitude but little tilted, so obviously you can see that liquid is flowing through this part and this part, the whole liquid what is passing through this is not passing through this imaginary area, something less is passing through this one. Similarly, if I further rotate it, for example, I have taken this area something like this. So, liquid is flowing this way and I have taken area this way, then there will not be any liquid crossing this area because lines will be parallel to the surface. So, if I ask how much liquid is passing through this area, then obviously it will be 0 in this situation and it will be something less as compared to what is passing through this one. So, depending on the way you have taken this imaginary area, you are going to get different amount of liquid passing per unit time. So, we need to have a quantity by which we can find out how much liquid is passing through this area. If I define this as area vector, here if I say this is dA vector and in this case it will be dA vector like this, and I am writing flux of liquid which is nothing but amount of liquid passing per unit time. So, this is nothing but d volume by dt as area vector dot velocity vector. Automatically this dot product will take care of how much liquid is passing per unit time. When this angle is 90 degree, like in this case velocity in this direction, area in this direction, 90 degree angle. So when I substitute 90 degree here, this quantity will come automatically 0. So for this area there is no liquid flowing per unit time, that is given by this expression when we substitute A vector mod V vector cos theta, theta is equal to 90 degree. In this situation assume that this angle is theta is equal to 60 degree. So I will write theta is equal to 60 degree. In this case I will get the volume flowing per unit time. So depending on the angle made by area vector with velocity, you are going to get different value of flux. When area vector is perfectly aligned with velocity, like in this situation area vector in this direction and velocity in same direction, then in place of theta you will be writing 0 and then you will be getting flux maximum. So depending on the way you have selected area, you are getting different flux that can be expressed in terms of dot product with area vector. So with the help of area vector we can easily calculate how much amount of liquid is passing through this one. Now consider a situation that I have got a point charge and from point charge field lines are originating and I want to find out how many lines are passing through a given area, how many imaginary lines are passing through given area. So I can extend the same concept there. In place of velocity now I need to write field. So this velocity will get replaced by electric field. Similarly, if I keep magnet and around it I consider imaginary area and I ask how many imaginary lines are passing through that area, then in place of electric field I can now place magnetic field. So the concept of flux is very important to understand what is happening in a space, right. Let us understand what is electric flux and how it is defined. So electric flux, if I take area like this and over the area I have taken a small element here and through this small area field lines are passing. Let field lines are making angle theta with the area vector. Area vector I already defined. With the area vector field lines are making angle theta, right. So the flux associated, just now I told flux will be electric field dot area vector. So through this small element the flux associated, electric flux associated is given by what is the field here, dot product with the area vector. Now if I want to find out total flux associated with this complete area, how much flux will be associated with this complete area, I will integrate and I will get the value. If it is uniform, if everywhere field is same, then so directly I can write flux is equal to field into area of the plate dot product, right. This is the total flux. If field is non-uniform, if field is changing, it is non-uniform, then we need to find the flux associated with a small area and by integrating I will get the total flux. So this expression we will use when field is non-uniform. If field is uniform, we can directly apply E vector dot A vector to get the value of electric flux. Similarly, to find out magnetic flux, this E will be replaced by magnetic field, right, B, that we will see later. So flux basic definition is clear. Let us take some examples so that we will understand how to calculate the flux. related to flux, see it is a scalar quantity, obviously this vector dot this vector will give you a scalar quantity. This is a scalar quantity, but it is a property associated with vector field. So field is a vector, but flux is scalar, and unit is this can be written Newton Coulomb multiplied to the area. By that you can find out the unit Newton per Coulomb into meter square. This is from this definition, F is equal to Q into E, right. So E is Newton per Coulomb, and that we need to multiply to the area vector, that is meter square. So unit of flux is Newton Coulomb per meter square, that we can also convert into Joule meter Coulomb. If I multiply and divide, or I simply take 1 meter this side, Newton meter into meter divide by Coulomb, this is nothing but unit of energy, Joule. So another unit is Joule meter per Coulomb. This is the unit of flux. Now let us see what we have learned. Flux is equal to field dot A. I am writing this one by assuming that field is uniform. So these all diagrams are representing uniform field. Now in this situation you can see that field and area vector, this is representing area vector and this is representing field. Yeah, this is area vector and this is representing field. In this situation you can see that there is no line crossing the area. So the flux associated with the area is 0. So phi is nothing but E vector mod A vector cos, here angle between field and area vector is 90 degree. So I will write 90 degree over here and cos 90 is 0. So this quantity will be 0, no flux associated with the area enclosed. In second situation, area vector and field both are in same direction. So I can write phi is equal to E A cos 0, 1. So flux associated in this situation is mod E mod A. For any general situation, here area vector is making theta angle with field. So flux in this situation is mod E mod A cos theta. So I hope now you are able to visualize, depending on the way area vector is there in space, there will be flux associated with the area vector or flux associated with the imaginary area, right. So basic definition of area vector is clear and its role in finding flux is also clear. So flux is given by a formula, flux, electric flux associated with given area is E vector dot A vector. If field is variable, we can integrate to calculate electric flux. What's the use of finding electric flux? Later we will see, but flux calculation can be done using this formula, right. Now let us take one simple example. I am placing one plane in a field which is given in 3 dimension. You can see 3i plus 24J plus 6K, right, and through the area 5 meter square whose normal unit vector, whose normal is in this direction. So, field is in this direction, which is uniform. And we may have area vector in this direction. So, because of this one, see, area vector is coming this way. So, fields are entering into the area leaving I hope now diagram is more clear. So, through imaginary area of 5 meter square, 5 meter square, electric field is passing, where the area vector, the normal to the plane. So, normal to the plane will give you the direction of area vector, right. So, area vector is in this direction. I want to find out how much flux is associated with this one. So, flux is equal to, as field is uniform, I can directly apply phi is equal to E dot A. E is how much? E is 3I plus 24J plus 6K dot area in vector form I need to write. Magnitude I know, magnitude is 5, and this is just giving you direction. This is just telling you area vector is parallel to this vector, but we require direction. So, from this vector we can extract the direction out, we can convert this into unit vector. So, converting this into unit vector will give me 2I plus 4J plus 6K divided by under root 2 square plus 4 square plus 6 square. Take 5 out, this 3I dot 2I will give you 6 plus 24 into 4 will give you 96 J cap, J dot J 1 plus 6 K cap dot 6 K cap will give you 36. So, this dot product over. Now, we divided vector from its magnitude to convert this into unit vector. So, what we are doing here, we are writing magnitude of area and then the unit vector to write area in vector form. So, to write in area in vector form, I have divided it by its magnitude. Now, this is 4, this is 16 and that is 36. We can simplify and we can get the flux. So, as field was uniform, just apply the formula and get the flux associated, right. Now, let us see another example. So, question says find the flux associated with a cube. So, first example, we have field is equal to 2I plus j minus 4k, that is uniform field, right. So, let us first see first part. If cube is placed in uniform field, how much flux will be associated? So, what I can do, as this is a closed one where all the surfaces area vector will be in different direction, I will calculate the total flux associated by finding flux associated with every surface. As flux is a scalar quantity, I can add them all to get the net flux. So, here I can see this front surface, this top surface, this right one, and then left one, back one, front one, and this bottom one. All these 6 surfaces I want to calculate flux. So, let us do one thing. For every area we will calculate the flux, right. So, what you can see I will name as odd, and what you cannot see, which is the back one and the side one and the bottom one, I will name as even. So, front one, if I take 1, then the back one will become 2. This top one if I take 3, then this bottom will become 4, and if this one is 5, then this left one will become 6. This is just for naming so that you can easily understand, right, what is there. So, for every surface I will define the area vector. So, if I take 3-dimensional diagram, see, so for this top one, this elemental area ds will be in this direction, and for this left one if I take, this will have area vector this way, and this left one if I take, it will have area vector this way. Similarly, at bottom if I take a small element, that will have area vector this way. I hope you are understanding. Visualize cube. So, there will be 4 surfaces, top, bottom, right one, left one. So, for top perpendicular to the surface we will define the area vector that will be along y axis. So, for this one I can write this as this is x axis, I will define this as dx. This inward, that is outward is z axis, inward is also z axis, this I will call dz. So, I can write ds this way, ds is equal to dx dz j cap. This bottom one will be opposite to this. So, here I can directly write dx dz minus j cap. This one, this I can write, see, this is towards y and this is inward, right. So, dy dz, this is dy and this is dz, I can write this as dy dz. As direction is towards right I cap, this will have direction minus I cap. These 4 we have done. Side one we have completed. The front one, consider a small element over here dy dx, the front one. Front surface dy dx perpendicular to surface k cap. Similarly, for back one I just need to write minus k, right. So, front one plus k and back one I need to just change the direction minus k, right. So, step by step we can find out the flux associated. Now, so if I ask what is the flux associated with first surface, see flux associated with first surface, area, if I assume that this is A, this is A, this is A, the area of this one in magnitude will be A square. So, field I will write 2I plus 3j minus 4k field, as field is uniform, no need to integrate, multiply to the area dot product A square for first one, the front one, A square outward minus plus k cap. So, k cap, this will give me flux associated with first one. So, k cap if you multiply, you can see minus 4a square you will get. Similarly, flux associated with second one, I just need to change the direction. Second one means the back one will have area vector in inward direction. So, I can write 2I plus 3j minus 4k dot a square minus k cap is equal to, this will become plus 4a square. Only difference is with sign. Similarly, flux associated with third and flux associated with fourth. Third is which one? The top one. For top one, area vector will be in this direction. So, this is A, magnitude is A square j cap. So, I can write 2I plus 3j minus 4k dot A square j cap, and the fourth one will be in front of it, bottom one. So, for bottom one, area vector will be like this minus j. So, here I can write 2I plus 3j minus 4k dot a square minus j cap. So, first, second, third, fourth, fifth and sixth, same way we can calculate 2I plus 3j minus 4k and 2I plus 3j minus 4k Now I need to do dot product with the area vector. Look at the fifth one. Fifth one is the side one, and it will have area vector along x direction, a square, area in vector form, I cap, and the last one, sixth one, look at this one. This will have area vector in this direction, minus I cap. So, here I can write dot a square minus I cap. If you add them all, you will get the total flux. Flux is scalar quantity. So, flux associated with 1, 2, 3, 4, 5, 6. Look at the values. This and this will get cancelled out. This is minus 4a square, this is plus 4a square. Similarly, here you will get plus 3a square, and this you will get minus 3a square. When you add, these two will get cancelled out. look at this one here, this value will come if you do dot product I dot I1, so this will be 2a square and this is minus 2a square, adding them will make it 0. So this and this will get cancelled out, this and this will get cancelled out, this and this will get cancelled out, and you are getting 0. So total flux associated with the cube in first case is 0. So first part it is coming 0. You can see that flux is associated with every surface, but when you add them all, total flux associated is coming 0. So flux, if we are asked to calculate individually, everywhere we are getting non-zero value, but when we combine that, it is coming 0. That means when a closed surface is placed in uniform or non-uniform field, here we have taken first uniform field, let us first talk about this one. When a closed surface is placed in a uniform field, the flux associated, total flux associated with the closed surface is 0, right. So this is very important result, just keep in mind, if field is given uniform and you are asked to find out flux associated with a closed surface, it might be cube, it might be sphere, it might be cylinder or cone, anything, whatsoever be the surface, the total flux associated will be 0, right. So this I have solved, this one you try. So tomorrow we will discuss what happens when we have a non-uniform field. Procedure is same, you can try on your own, right. Tomorrow I will take up this example and we will talk about what happens when we have non-uniform field. So I hope you enjoyed today's class. Thanks for watching.